I'll just get started. So we started off in the morning with the first group of SMEs that talked about all their experience and at the practical level, what they actually did. Now we're going to talk, that was more about modeling and simulation services and such. Keep on going. Now we're going to get into another cool part, which is about lasers in manufacturing. Now, I am quite interested to hear about this because I'm a bit of a Star Wars fan. Did you actually know that there's going to be a next Star Wars follow-up movie at the end of this year, sort of a Star Wars 7? And they've actually changed the lightsabers, you know, that it's two-sided now. So from a laser perspective, that should be pretty cool. But we're going to talk about other insights today. And to kick it off, we have Ulrich Tombansen from the Fraunhofer Institute. And he's with the Institute of Laser Technology. They provide solutions and services in the field of process control and system technology and such. And he coordinates the LASHARE project, aimed at establishing accelerated laser technology transfer by means of conducting laser-based equipment assessments. Now, I am curious to hear if that's a risky business or not, but I leave the floor to you. Thank you.
It is a challenging business, because one of the things that are special about this laser equipment is that in most cases you do not see the laser. There are some green lasers out there, those you can see, but most of them are in the infrared, so you do not see the tool that you're working with. But still, if you look at all this setting, all this environment, would you think that laser is involved in that one? It's not directly contributing to it, but the molding tool that does this injection molding process for the plastics, that one is extremely enhanced by drilling micro holes for ventilation. So as soon as you push in the warm plastics into that form, it can go in much faster when you drill holes into the form. A solution is developed within LASHARE that enables this technology to be used, so that we're talking about an enhancement in production speed of more than 70%. There's another application area that's microstructuring, so you can change the property of surfaces. That's done with these nice things. That's a replication process, so you change the surface of a die and you press coins with it. So you have completely new features on these coins, and Clemens is going to talk a little bit more later on about this project. Lasers can also be used for creating shapes. So here, for example, we're talking about thin film processing. So you have a plastic substrate, you put some metal on top, and you change the properties of that metal to give you a shape. We're talking about using of ultra-short pulse lasers, which are pretty much expensive. If you split the beam into multiple beams, like you see on the bottom left, with these 4 parallel processing steps, the equipment that you need for it is on the top right. So this is this kind of structured diffractive optical element. Then you have 4 beams at the same time. So it can change from processing speed of 1 to processing speed of 144 if you use 12 by 12. So that are the challenges, that are the changes. Another thing you might have heard about is 3D printing. So you can create today products that have internal structures that you cannot manufacture by any other process. That's going into serious production for GE in fuel nozzles. We talk about protective coating. So you blow in powder, you heat it with the laser so that it sticks to the surface of something. You have a big problem if you try to do that for an inside tube. So what's being developed is a very, very long optical system that provides this coating technology to a tube of a diameter of 50 millimeters and 1.5 meters long. So those are technologies that are samples of industrial applications that serve a wide market and that might even be exploited to other areas. And that is the focus that the currently implemented laser projects in I4MS are for. Looking at the market, laser equipment, the rise is quite immense. We're talking about, it depends on who you ask, but most of them agree that we are somewhere between 5 and 8% of growth. and that is a sustainable market growth. There are coming out new applications every day, like, as I just showed you, thin film processing as new performances with ultra-short pulse lasers, which enable new technologies, and the changes are quite significant in that area. The first project in this row is the Apollo project. They have set up their concept of being a hub of application labs. So they have 5 laboratories, 7 users, 7 suppliers, and they focus mainly on microprocessing. So that's thin film processing, surface texturing, and patterning. The other project is LASHARE, and in LASHARE we try to implement from the base of having joined 6 renowned research partners to a LASHARE competence center to provide something what we try to call assessment circle, an assessment methodology. So to look at the equipment, to look at its transfer to production and the requirements that it needs to go from a lab demonstration to a robust prototype. How does I4MS now help? From our perspective, from what we see today, is that this communication between user that is going to represent the market, the supplier who has got an idea but does not have access to industrial application, and the research partner, if these 3 sit together and really jointly try to develop and to put forward a new solution, that this, with the backup of the scientific stuff, really leads to an accelerated technology transfer. So when they agree on challenges and solutions, they have measures in force to validate the achievements. This lowers risks and barriers. So that's what we were talking about, to lower the entry risk of suppliers to enter a new market, to bring out a new equipment. This lowers the risk of the user to buy a new equipment, to introduce it into its company. And so that helps both sides. What we see today is that there are already revenue streams from the publicity that the SMEs gain from that they have already requests for new products, so they already add stuff to their companies, and that they currently start to focus on their exploitation and even on extension to new application areas. So how are we going to take it forward? You all heard about the competitive calls. Apollo has, at the change time of this September, because we are a little bit behind the timing of the other projects as we started in September 2013. So in September, we will have 8 validated applications for Apollo, and Apollo will implement 6 to 8 new applications in their framework. LASHARE will have 14 assessments finished off, and we'll try to implement 12 to 14 new LEAs at that time. And we're going to have a new event at Laser World of Photonics, where we try to talk to all the participants of the market, so to the users and to the supplier side, and to present what's currently going on in the I4MS funded projects, but also in the other projects. So also this brings together the value chain of the users, the suppliers, and the helping or assisting research partners. So that's all I wanted to talk to you at this moment, and I would like to hand that back to Dinant to introduce the speakers that are going to be a bit more in detail and a bit more specific, and also provide some figures to you. Thanks very much.
So the expectations after this morning are quite high, given the diversity. And the first speaker I want to invite up is Jordi Garcia from Monocom.
Okay, once I was told that when you are presenting something, you got a KISS. KISS stands for keep it short and simple. So today I will try to KISS. Unfortunately, I'm not Jordi Garcia. today. Jordi Garcia is our R&D director in our company. Some of you know him, and he has recently become father, and that's why he cannot attend today this meeting. So I'm Carlos Uriac, the sales director of the company, and I will replace him, just because Jordi, at this moment, is dealing with something that is probably more important than this. Sorry about this, but that's the truth. In fact, when you become father or mother, your awareness of risk starts to improve a little bit. So you start doing so many things, and one of them ends up buying a safer car more normally, bigger and safer. And that's what we are doing here in this project, in fact. Because in order to increase safety in cars, you need safer parts, more robust parts. In fact, one of the main components of cars is the steel, and you most probably know about it. So if you want to increase the safety of a car, you need a harder steel. But you, at the same time, need to work with it, shape it, deliver it to the exact form factor you need. And one of the drawbacks when you play with this hard steel or higher strength steel is that although it's harder for resisting impacts, it's also harder for working with it. You cannot bend it easily. And things that do not bend eventually just break. And it's what normally happens when you try to roll form a steel. We have a short video. Well, in fact, it's not that short. It's a 2-minute video, but we'll try to keep it shorter, showing you how steel is normally formed. And you have these big rolls where the steel stripe goes by, and it's starting to get bended gradually. So this is the main point. But as I was telling you, when this is done at a cold temperature, this steel will break. If you try to heat up all the sample, the whole sample, in order to help this bending process, you change the material properties. And changing the material properties means that you will lose some strength of this material. And if you try to heat it locally, but slowly, like is the current techniques right now, you don't achieve the degree of the performance that you will need. So what can you do here? And what we did, in fact, sorry about that. I just clicked on the same position of the slide. Here, we developed a laser, a diode laser, that is directly applying on the sheet, the metal sheet, as when it is really working. So this should be like a normal roll forming station. And here you have a picture of the laser that is heating up locally the zone. So what you achieve is a very fast temperature raise in a very small area of the steel that helps you bend it. So you can start working with this steel that up to now it was just impossible to work with. So we did it with a new development thanks to the technology that Monochrome has, that it has some advantages. Monochrome is the company I work with. And we have a that is capable of delivering laser bars with no smile. That picture you see on the upper right side of the slide, where we are comparing a normal laser bar versus a clamped laser bar mounted with our technique. So as you can see, this is completely flat. And when this bar is completely flat, you can do things like this one in the lower part of the slide, combining lots of these high-power lasers in order to achieve extremely nice beam profile, very nice line in the metal sheet. So you can work exactly on the area you need. So this was bringing our technology to a new application field for us. Monochrome is an SME based in Barcelona. We are only 35 people working high-power laser diodes, and we are mainly working in the medical field. Okay, we have some applications also in space, but we are mainly working in the medical field. So we had no experience in material processing at all, nothing. And of course, we didn't know anything about the potential market of it. In fact, we normally thought that laser diodes are not really useful for material processing. Other kinds of lasers are normally used for material processing, not ours. So what LASHARE brings to us, what FLIT brings to us, is the opportunity of start working in a new field of applications that in fact is huge. I mean, our annual turnover is like 3 million euros. The impact that this project can have for Monochrome is about 10 million euros. So just imagine, for a small company with no access to big customers, with no access to this market, with its mass-consuming market of like the car industry, can this kind of project represent? So this was really helpful, because the component manufacturer don't usually know how his technology can work in a different environment. And in fact, we just discovered that the power level you need for metal tempering is just the same that you need for hair removal, so, which is one of our main strengths. And it's surprising, but right now it opened a huge new field of applications for us. How did it come? Well, our partners in this project know what do they need, roll-forming metal sheets, high-strength metal sheets. Another partner knows how to do it. What do we need? What parameters are required in order to do so? And they already know that we existed, luckily. So that's how we joined it with our technology, this project. So really, the scheme, this financial scheme is really helpful. And I think that the main message that I should be telling to you is that, yeah, maybe I am not keeping this presentation really really short and simple, but LASHARE was a real kiss for Monochrome. I mean, it improved ourselves. It made us learn new skills that we will apply in the future, and we are still not ended with this project, because right now we are learning what the big industry wants. So now we are integrating new signaling in this laser head. Now we know what kind of interfaces do they normally need. Now we can explore other material applications that we even did not know before joining this project. So the main idea I would like to bring today here is that these kind of schemes work. These kind of schemes help small companies to access big markets, to have more knowledge, to hire new people, and in fact, in places like Spain, 70% of our GDP comes from SMEs. So please, keep supporting SMEs, because for a country like ours, with this kind of economical situation we have right now, these kind of things can make a real change. Thank you very much.
Thank you, Carlos, and also thank you for taking over for Jordi, who's now who has just become father. Next presentation is Andreas Mikhailovas, and he's the science director of EXPLA, manufacturer of lasers, laser systems, and laser components. So I think the next episode of Star Wars is for you.
Thank you. Good day, everyone. I'll starting presenting another one project, Apollo project. As was mentioned, it's a project in which scientific labs assessed laser equipment for certain kind of the technologies. And what we achieved in this project is, as for you, for non-laser people, our achievement with a picosecond laser with 1,342 nanometer wavelengths sounds quite curious and not very interesting, but for people who are involved in semiconductor technology, this wavelength it's very attractive, because silicon is transparent for this wavelength. And there is a lot of possibilities to machine silicon wafers from all sides. It's just introduction. And For audience, is not very interesting what is inside this box. For laser people, it's more interesting what is outside of this box, and we succeeded to make a quite powerful laser, which is attractive for using keys in laser technology. With quite high repetition rate, which could assure good manufacturing speed, and a lot of control regimes was realized in this laser. And one of the challenges was to make synchronization with quite modern devices like polygon scanners. About development of these scanners, the next presenter of our project will tell for you. But as this laser was very interesting for semiconductor technology. The validation was done on the semiconductors which were used in thin film photovoltaics batteries. The job is just started, is not final result yet, so I will not inform you about something with very brilliant results, but there is some information that it could be really attractive. And if laser people took this big toy in their hands, they start to experiment far. Not only with this particular wavelengths, we started to tune this wavelengths in different spectral ranges and got colored radiation from this laser too. How we did it? Many